Hello, I'm Fellner.
And I'm Anette Messinger.
We are quantum software engineers at ParityQC, and they are leading the co-design team together. Our goal at ParityQC is to pave the way to implement our architecture on various hardware platforms.
Even though it was originally developed as a mapping for optimization problems, the parity code can also be understood as a stabilizer code, where the exact encoding is defined by the parity constraints.
In this case, for example, the encoding is defined such that the product of the eigenvalues of two qubits, for example these two, which are either plus or minus 1, is the same as the eigenvalue of the third qubit, or in other words, the product of all three is always plus 1. We say that this qubit represents the parity of the other two, which is why it is also called a parity qubit.
In terms of quantum operations, this means that certain many-body interactions, like for example the so-called RZZ gate, can be easily implemented by applying a single local operation on one of these parity qubits. Other interactions, however, can get quite hard to implement in this code.
An easy way to implement a universal gate set is to use arbitrary single-qubit interactions, which are always easy directly on the qubits without a parity encoding, and in addition, Ising-type interactions like the RZZ gate, which is easy in the parity encoding.
So the idea is to split the algorithm into blocks of gates which are implemented in the parity encoding and other blocks which can be implemented directly on the qubits. Then we can always switch between the two stages or even between different kinds of encodings that allow different interactions.
We recently developed a method that allows us to do this switch with a constant time overhead by using measurements and classical information processing similar to the quantum state teleportation protocol.
Just like in the idea of quantum repeaters, a single round of local entangling gates, followed by measurements, can create long-range entanglement over arbitrary distances. With a final round of spin or phase flips conditioned on the measurement outcome, we can then transform our state to the desired code state.
For example, this measurement-based approach allows us to perform the quantum approximate optimization algorithm, short QAOA, in constant time, regardless of the system size. That is an important step towards achieving quantum advantage on devices that will be available in the near future.
As you can see, the potential of this technology is very exciting, and we can't wait to see where it goes from here. Thanks for watching.